Welcome to the fourth video of our Relations module of our Discrete Math Review for Foundations of Computer Science. This video will be about partial orders. Like equivalence relations, a partial order is a special kind of relation, and we can define it using the properties that we discussed in the previous videos. So a relation is a partial order if it is reflexive, antisymmetric, and transitive. So you'll notice that's very similar to an equivalence relation with the one major difference that it is antisymmetric instead of symmetric. And so hopefully you'll see that that change has kind of an interesting effect. Okay, so let's look at some examples. The first one look at is our pre, which remember we talked about before in some detail. Remember we did define this as xy such that y is equal to xw for some w in S, where S is some set of strings, right? And it turned out that this meant that we were talking about a string x that was the same as the beginning of y. And so we could add some string w to it to make it equal to y. And so therefore, x is a prefix of y. So this relation is a partial order. And we have to check our properties to make sure that's true. But we want to ask first, okay, is an element in this relation always related to itself? So in other words, is it a prefix of itself? So before I do anything too fancy here, I think I should probably just look at an example and see, what seems reasonable. So let me think of some string. Maybe my string is ABA, right? And I want to say, is that related to itself, ABA, under this relation? Well, it would be related to itself if the first string here, our x in this tuple, is equal to the beginning of the second string. It is definitely equal to the beginning because it's equal to the whole string, right? So A is here, B is here, A is there, so that matches up, and I'm allowed to kind of go as far until I've run out of letters of that first string. And so this works, and it's pretty hard to see how there's going to be some example where it's not going to work. So that's good. It's always good to believe the thing that you're trying to prove is actually true, but how do we write it more precisely and in the general case? Well, we can use the definition and say, well, for any element x, I need to be able to find some w such that y is equal to xw, but in this case, I know that my y, because I'm worrying about reflexivity, is actually going to be x. So I want to say, is it possible to find a w that makes this equation true, right? In this case, I do have to be careful about how I defined my s, right? S, in order for me to be expressing the notion of prefix that I'm really thinking of here, S had better include the empty string, because that's exactly the string I'm going to use. I'm going to say I can always choose W is equal to the empty string, and that is going to make this equation true for any choice of X. And so now I have in fact demonstrated generally that this has to be reflexive. All right, so I'm going to skip over anti-symmetry for a moment and move on to transitivity, and we'll come back to anti-symmetric property in a minute. So for transitivity, again, let's pick some example first. Let's say our first string is bat, and we have a relation between bat and battery. And that's a prefix relation. And, maybe I'll just say bat and batter. That's even better. We'll have real words we can use. Say bat and batter, and then I have another relation between batter and battery. And then the question is bat related to battery? Is it a prefix of battery? And yes, it is, right? So that's an example that sort of seems to support this theory, right? We can keep this, and it sort of suggests that this is going to be transitive in the general case, as our prefix of, as this string kind of gets longer, this prefix has to continue to be a prefix for everything that this our y here, that our batter is a prefix of. So kind of getting tripped up in the particular example. So let's move on to making this more general. Right here is our x and our y, and this is our y and our z. And now we're asking about, does that always imply x and z, right? All right, so we've now assigned variables, and it's slightly more general, and let's now translate it into the language of our definition. Why exactly is x related to y in terms of our definition? And that's another way of saying, what is our w? Well, if x is bat, I have to say that's equal to batter. If I've added, put it in another color, this w, well, clearly in this case the w is ter. Right, so let's do exactly the same thing with our pair y and z, right? So we said they are related, and we have to say that means that batter is equal to battery if we add a string w on the end. In this case, w is very short. It's just that y, right? All right, so we have a little bit of an awkward situation here because I used w twice, right? I used it, and I used it to represent different things. Over here it's ter, and over here it's a y. So to distinguish them, let's make it w prime the second time. So now here is the good part. We can use these variable assignments we've made to look at our final pair in our example and understand a little bit about why it works. Remember we said, okay, bat is certainly related to battery, but in our language, why, right? Well, let's write it out. So we said that means bat plus some w is equal to battery. All right, what's our w? And we'll have to change this. Maybe we should call this w double prime here, just to say this is the third one. In this case, it is t e r y, right? But we can go a little further with that because we already defined a variable for ter. We already called that w. And we already defined a variable for y. We called that w prime. Right? So if we now go back and substitute everything, my bat, remember, is the x, and battery is a z. So what I really said is that I am relating x and z through by adding to x w and w prime, right? And what I'm showing here is that I can always construct that, right? Because I have my w is always emerges from my first relation by the virtue of there having been a relation, and my second w always emerges from the second relation. Sorry, my w prime always emerges from that second relation. And when I concatenate them together, I get exactly the string I need to produce that third relation. So that is kind of the essence of the proof that this is transitive. All right, I'm going to clear the screen for a minute, and then we'll look at anti-symmetric. Okay, I'll use the top of the screen here, and this is actually not bad at all. I didn't mean to suggest that it was difficult, but I just postponed it because I wanted to recall the definition and kind of go through. Remember, anti-symmetric, the definition is that if x is related to y, and y is related to x. So if it looks like there's about to be symmetry, right? Oh, I should say in R here. Then it means that x is equal to y. So then it means that actually we're seeing an identity. And that's what this rule kind of indicates in general. And let's look at an example here. So what would it mean for a prefix relation to seem like it's about to be symmetric? In other words, to say, okay, well, let's pick some, if I pick some strings here, A and ABBA. Well, certainly A is a prefix of ABBA, but I definitely can't reverse that because ABBA is going to not be a prefix of A, right? So it is hard to think of an example where this is going to work, except in the case where we actually just use the same string. And that's not a very strong piece of evidence, but you can definitely see, let's see if I go AA, right? Okay, that'll work, but it's hard to even see what's happening there. So let's do it symbolically. In this case, I think it actually brings more clarity to what's going on. If X is related to Y, then we'll just keep using our regular definition. That means X equals Y, where we've added some W, right? And if Y is related to X, then we just reverse that. We say X is equal to Y. And of course, no guarantee that this W is the same, so we'll use that W prime just to mark that this might be some other W, right? Okay, so if we have these two things are true at the same time, what does that tell us? Well, I can now do some substitution. I can take this X, I know what it's equal to, and just plug it in here and see what it gets us, right? So Y is now going to be equal to Y, W prime, that's the substitution, and then W, right? So I can see pretty easily that the only way that Y is going to be equal to Y plus two other strings is if W prime is equal to W is equal to the empty string. Those both have to be empty. And so now that I know that my initial equations, what I really just wrote was X is equal to Y concatenated with the empty string. And that implies, of course, that X is equal to Y. So that does prove this is true in general. And we've now demonstrated that this is also antisymmetric. That is a pretty detailed explanation of why R pre is a partial order. So now I'll show you a few more examples of partial orders, and I'm not going to explain these in anywhere near as much detail, but hopefully you can extrapolate from this first explanation and maybe write your own and satisfy yourself that these other relations also meet the criteria. They satisfy these properties that are required to qualify as a partial order. Next example I have is the substring relation. This also is a partial order where X is a substring of Y. And for very similar reasons, also the subset relation. When we say something is a subset of another set, that gives us a partial order. And then finally, the suffix relation. This is the relation where, in this case, I've written Y is a suffix of X. Y is equal to the ending of X. This is a partial order for very similar reasons that we saw when we were looking at the prefix relation just a minute ago. So before we move on, it's certainly worth taking a moment to reflect on what these examples qualitatively have in common and why maybe partial order is a good term to describe the kind of relation that they define. So just use the substring example first, right? Say we have some string A, B, C, D, E, F, G, H, right? And we have another string that is a substring of it. We'll just take B, C, D, E, F, G, and then a string that is a substring of that string. So that would be, let's say C, D, E in this case, and then we'll just take D, right? D is a substring of that. Because this is a partial order, one of the things we can kind of rely on is that if D is a substring of this string just above it, it's going to be a substring of every string in here, right? In other words, and that's true too about the next string up, right? Our C, D, E here is going to appear in everything above it in the way that I've written. So what we're saying is that this relationship defines an ordering over everything that is actually related. It doesn't guarantee that things are related, but if they are related, then we have this kind of nice ordering, and that comes a little bit out of the transitivity property, right? Another thing that we see in partial orders, something they're often used for is that the antisymmetric property tells us that if two things are related to each other symmetrically, so if we say if x is a substring of y and y is a substring of x, that turns into a proof that x is equal to y, and this is a way we can kind of identify elements that are the same. Likewise, you've definitely used, I'm sure, the mutual subset relation to prove set equality, right? If two sets are subsets of each other, then they're equal, right? This is kind of something you get from partial orders. And by the way, I'm picking examples here that are very related to our particular problem space, but other kinds of math classes out there often talk about, say, greater than or equal to, or less than or equal to, or divisibility when they're talking about order relations, and those may be familiar to you as well. So that wraps up our review on partial orders. We have one more video on relations coming up, and that will cover operations for combining relations.